Learning a language from a textbook gives you vocabs in isolation. You memorize chair, but you've never seen it in the room you're actually sitting in. And Locale brings language learning into the real world, moving vocabulary out of textbooks and into your actual environment. Built from scratch as an installable progressive web app using React, Spring Boot, and AWS, it connects you to your surroundings and community. You can instantly translate physical objects using an ML-powered camera scanners, meet up with nearby learners, and share real-world vocabulary on a social feed. By combining machine learning with community, Locale smoothly bridged the gap between memorization and everyday life.
Hi, my name is Hoàng Mạnh Nguyễn, and I'm in charge of explaining the architectural overview about application. Locale is a progressive web app. We started as a React web application, then packaged it for browser installation on any device. It runs on 4 services: React TypeScript frontend, Spring Boot backend, PostgreSQL, and Fast API for machine learning service. The backend writes media to S3 via AWS SDK. Users read media through CloudFront Cloud Delivery Network, 2 completely separate paths. The key architectural decision was isolating the vision service. Machine learning frameworks are heavy, and this lets us update the machine learning stack independently. Here is Vision Service Client. The endpoint is injected via app value. The backend reads it from App Vision endpoint, which maps to Vision API URL in the environment. Porting to the backend at a different Vision host requires changing one environment variable. No recompile needed. The image and language code are sent via HTTP post. If the Vision service is unreachable, REST client exception is called here and thrown as object detection unavailable exception. The global handler maps that to a controlled 503 error. A failed scan never crashes the application. The back degrade gracefully. Inside backend, 21 controllers are grouped into 7 feature domains. All HTTP traffics pass through the JWT filter. WebSocket frames go through the channel intersector.
Now that you've seen how the 3 services connect, let me take you inside the scanner, which is where most of the engineering decisions happen. The scanner is the entry point for vocabulary, where users pick up new words from their surrounding area. We initially looked at Zolo as a detection solution, but the problem is Zolo AT classes are too generic for language learning. A learner needs precise vocabulary like espresso cup or a teacup, not just cup. So we built a custom detection pipeline that's used together with our Google Vision language model to get that level of specificity. The pipeline starts when Fast API receives the image. Zolo's only job here is to find where objects are. It gives us bounding boxes, and we take the coordinates never touch the class label. Each box is then expanded by 20% to avoid clipping the object at the edges, and that crop goes into SIG here. SIG was trained on image text pair, so it understands the meaning of what it sees, not just the pixel, and it converts the crop into a high-dimensional semantic vector, then we auto-normalize it. That vector is what we search against our taxonomy. Then come to the retrieval phase. It happens in 2 stages. The first one is coarse root, where we compare the vector against 10 category centroids, things like furniture, kitchen, and electronic, and that returns the top 3 most relevant categories. Then we move to the fine retrieval phase. Inside these 3 categories, we've run a full-phase search across all matching concepts, top 5 per category. At 800 vectors, exhaustive search is faster than any approximate method, and we get exactly result. The output is a ranked list of concept candidates with similarity scores. Now this is the phase we designed ourselves. Since one photo usually has multiple objects, Zolo gives us multiple boxes, and each goes through the full SIG and phase pipeline independently. So at this point, we have multiple results and we need to decide which ones to trust. We score each crop by 3 factors: how central it is in the frame, how large it is relative to the image, and how complete the objects look. A well-framed, fully visible object score higher than a small background. Then context re-ranking. If multiple crops independently agree on the same category, that category gets a 1.5 boost. Agreement across crops is a strong signal, so we amplify it. Results then go through a 2-gate filter. First one is that the best score doesn't clear a minimum threshold, we return unknown. And gate 2, the top result must beat the second best by at least 2%. Since 6 scores in fine-grained domain are very close together, for example, bar stew and stew might differ by 0.00. If the system can confidently separate them, it abstrains rather than guessing. Then come to the translation phase. Translation for the 4 primary languages run entirely inside Fast API, prebuilt JSON files uploaded as startup, and single dictionary lookup with zero network call. And for other languages, Spring Boot handled the fallback. So to put the full pipeline together, Solo segment the frame into candidate reasons and convert the reason into a semantic vector that captures what the object actually is, while face matches the vector against 800 concepts in our taxonomy. Crop importance scoring weighs the result of crop multiple decision. The model are open source pre-trained component, and what we build is the retrieval architecture on top of them, the taxonomy, the multi-cropping scoring, and the confident logic that turn them into a language learning feature. So that's for the scanner feature. Now Huang will walk you through the geo feature.
On this diagram, the flow starts in the browser with geolocation. Once the user allows access, the front-end gets latitude and longitude, which persists through patch API users, me, and then the request nearby learners through get/API learners nearby. The important part is that the backend does not run everything directly. It first calculates the distance using the Haversine formula and then applies the privacy rules to public, friends only, and nobody before renders anything on the map. To show how that is implemented on the front-end page, this is Explore page. Here's the app called browser geolocation. Stores the coordinates in a state, persists them through update profile, and then use these coordinates to load nearby learners. On the backend side, this is learner service, which contains the main business logic. It loads accepted profiles, friends ID, and then calculate the actual distance from with the Haversine formula, and then run a sorted list of learners who that the current user is actually allowed to see. So the key technical point here is that privacy is enforced server side, not just hidden in the front-end UI.
Here we have Docker Compose dependency chain. PostgreSQL uses a name volume. Data persisted across restarts without reseating. All back secrets are runtime environment variables. The Google Places key is the exception. It is a void build argument baked into the front-end bundle at build time. Here we have compose.fi. The backend depends on block enforces health conditions. It will not start until both PostgreSQL and the Vision service pass their health checks. This health-gated startup was a deliberate design decision to eliminate startup race conditions during development. Next, we have S3 storage model. S3 bucket is private. Only CloudFront can read it from via origin access control. 3 upload folders enforce separate size limits. Image at 5 MB, audio at 20 MB, and video at 100 MB. Here we have S3 service.java file. In S3 service, the key is folder, universally unique identifier, and sanitized file name. Put object writes the file to the S3 bucket with the bucket name, key, and content type. What the method returns is the CloudFront URL, which gets stored in the database and served directly to user.
So our testing focus on backend correctness and making sure the system handles failure gracefully. We have 30 backend test classes covering both the API layer and core services. The most critical one check that if the Vision service goes down, the backend returns a proper error instead of crashing, which is important for a stable user experience. The ML pipeline was also manually verified to confirm it was running and producing correct results. Ultimate front-end tests are planned as a future work, but the front-end was manually tested during all demo preparation.
So that's Locale, a full-stack language learning app built entirely from scratch. The 3 core technical pieces: an AI scanner that identifies the real-world object using custom YOLO, cyclip, and face retrieval pipelines. Geo-based meetups that connect nearby learners using server-side Haversine distance with no location privacy controls. And a real-time social layer over WebSocket Stomp. From here, the natural next step is expanding the taxonomy from 800 to 3000 plus concepts that cover more of what a learner actually encounters in daily life. And that's all. Thank you for watching.